So we will wait for some more minutes before starting. I will share the slides. Is the slides visible?
Yes, ma'am.
Okay. So good evening all. Welcome to problem solving session on week 4 assignments of the NP course Introductory Organic Chemistry II by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself Anisha Suresh, PMR of TA for this course from IIT Bombay. So today we will be discussing as two parts. We will be having a brief summary regarding what was discussed in week 4 modules, followed by we will be solving some previous year assignment questions. Okay. So now coming to summary of the week 4. In the topics that were discussed were carboxylic acid and its derivatives, then reactions of carboxylic acid and its derivative, and briefly we have discussed regarding the alcohols, ethers, and epoxides, and a special topic, E1CB reaction, was also discussed. So, coming to carboxylic acid and its derivatives, so this is the structure of carboxylic acid. Okay, R double bond OH. This is the structure of carboxylic acid, and if this OH is replaced by any groups, then that is known as carboxylic acid derivatives. So we have seen some examples of carboxylic acid derivatives like acid chloride, acid anhydride, esters, amides, etc. Okay, so in case of acid chloride, this X group will be Cl. In case of anhydrides, it will be RCOO, double bond O minus. And in case of amides, it will be NH2, and in case of esters, it will be OR. So we have seen the reactions of carboxylic acid and these derivatives in the lectures. Now, coming to discuss regarding the structure, carboxylic acid is having a or carboxylic acid or its derivatives is having a trigonal planar geometry. So substitutions at trigonal planar carbonyl groups, they go through a tetrahedral intermediate and then onto a trigonal product. So initially the starting material is trigonal planar in geometry, and the resulting product is also trigonal planar, but during the reaction it goes through a tetrahedral intermediate. So how it is taking place, so this carbonyl carbon is the reactive center, so nucleophile it will add on to the carbonyl carbon, the CO double bond will break and the electron density will shift towards, so it will result in the formation of this tetrahedral intermediate. Okay. Now, once the oxygen lone pairs will fall back, this X being a good leaving group, it will leave, leading to formation of the product. So ultimately, this X is getting substituted by the nucleophile. So how this existence of tetrahedral intermediate was confirmed? It is through this oxygen labeling experiment. So if we are having an carboxylic acid derivative where this oxygen carbonyl oxygen is labeled as O18, so in the presence of water, what will happen? Water will add on to this carbonyl carbon, a tetrahedral intermediate will be forming, and while that is breaking down, X will leave, leading to formation of this carboxylic acid. Then like in the presence of a base, this can undergo resonance, and this oxygen can scramble between this two carbonyl groups. Okay, rapid migration of the hydrogen atom between these two oxygen atoms by resonance. So how it is happening? So we are having this carboxylic acid derivative, then water will this electrophilic carbon sender, this carbon oxygen bond will break, and it will lead to formation of O minus, and this is the tetrahedral intermediate that will be resulting. Now a rapid migration can take place between the oxygen, this oxygen atoms. So this OH2 from this proton can go to here, leading to formation of O18H, or it can be two proton migration or proton transfer can take place, leading to formation of this OH2 plus, where oxygen is 18 labeled. And once this tetrahedral intermediate will collapse, then this X minus can leave, leading to formation of this, here the oxygen is O18 labeled, and this upon deprotonation we will get this carboxylic acid product which is having oxygen labeling. Okay, in some cases while um, falling of this O minus, this water can also remove, leading to formation of the starting material without this labeled oxygen. Okay, so this experiment is thus confirming that the reaction is going through a tetrahedral intermediate, because the starting material was initially O18 label, and here the product whichever is forming is not having the label. So for that to happen, this O8 carbonyl oxygen bond should break, and it can happen once it is mechanism only. Okay, any doubt regarding this?
No, ma'am.
Okay, so here basically an addition reaction is taking place, followed by elimination of the living group, leading to formation of the product, similar to carbonyl reactions we have seen in the last week. Now coming to reactions of carboxylic acid and its derivative. So for reaction of carboxylic acid to take place, the condition that it should follow is, if this reaction is to go, the carbon, this is the carboxylic acid derivative, the Y minus is the nucleophile, and it is resulting in the formation of this product where the X is getting replaced by Y minus. So for this reaction to happen, this X must be a better leaving group than Y, otherwise the reverse reaction would take place. If X is not a better leaving group than Y, then Y only will eliminate and we will get the starting material back. Y must be strong enough nucleophile to attack the RCOX. So it will be good it should have a good nucleophilic character, such that it will come and attack on this electrophilic carbonyl group, and RCOX must be a good enough electrophile to react with Y minus. So these are the conditions that should be satisfied for this reaction to occur. Okay, and this is the reactivity order for acid chlorides to amides. Acid chloride is more reactive and amides is the least reactive. So in between, acid anhydrides and esters will be coming. So this is depending on the stability of the leaving group. So Cl minus, this R double bondo O minus, this RO minus, NH2 minus. So depending on the stability of this leaving groups, this reactivity trend is coming. So this, its conjugate acid will be HCl, this will be R double bondo OH, this will be ROH, this should be NH3, right? Conjugate acids. So the pKa value for this will pK order will be, this will be having lower pKa than this and than this. So ammonia will be having near about 30 to 35, ROH will come around some 10 to 15 region, and this will be coming around minus 5 to 7, that range. So depending upon the pKa values, and the stability of these conjugate bases, this reactivity trend is coming. So acid chlorides will be most reactive than acid anhydrides. Acid anhydrides will be more reactive than esters, and esters will be more reactive than amides. So this is the reactivity order of carboxylic acid derivatives. This is clear. So,
Yes, ma'am.
so here when we are considering pKa, this will be having low pKa, and this will be having high pKa. Okay. Now coming to reaction. So since acid chlorides are more reactive, it can react and it will result in the formation of anhydrates, or it can react and result in formation of esters, or it can react and result in formation of amides. And in case of anhydrates, anhydrates can react and result in the formation of esters, and they can react and result in the formation of amides. In case of esters, it can react resulting in the formation of amides. Okay, and these all can react and result in formation of carboxylic acid. If acid chlorides are reacting with this R1CO2 minus, it will result in the formation of anhydrates. And if this anhydrates are reacting with any alcohols, it will result in the formation of esters. And if it will react with ammonia, it will result in the formation of this amides. Okay, and similarly, carboxylic acid also can be converted into each of this. If carboxylic acid is reacting with this SOCl2, that is thionyl chloride, PCl5, oxalyl chloride, etc., it will result in the formation of this acid chloride. And if it is reacting with this alcohol, etc., it will result in the formation of this esters. So similarly, all of these are interconvertible, and this will be the most reactive among carboxylic acid derivative, and this amide will be the least reactive. Okay, and for converting this amide into carboxylic acid, we need the presence of a strong acid or a strong base. Is it clear about the reactivity trend we have discussed? So based on that trend only, this reactivity is happening. Okay.
Yes, ma'am.
And briefly, ma'am have discussed regarding this alcohols, ethers, and epoxides. So a major reaction that was covered in that part was Williamson ether synthesis. So in that case, we are having an alcohol, and in the presence of a sodium metal, it will result in the formation of a sodium alkoxide. So this will be much good nucleophile, and hydrogen gas will be liberated. Now the sodium alkoxide, it can react with any alkyl halides, so preferably it should be primary or secondary, because the reaction will be taking place sort of SN2 mechanism. So for that SN2 trend, for SN2 reaction, the trend will be like primary more reactive than secondary than tertiary. So preferably it should be a primary alkyl halide. Then this alkoxide can add on to that carbon, and halide will be leading to formation of the ether and sodium halide. Okay, so alcohols react with sodium metal to form the conjugate base sodium alkoxide and releases hydrogen gas. And sodium alkoxide is added to primary alkyl halide to form the desired ether along with sodium halide. Is it clear? Williamson ether synthesis.
Yes, ma'am.
Okay. Then a special topic that was discussed regarding this even CB reaction. So in even CB reaction, so here this is our substrate that can undergo the even CB mechanism. So first a base can abstract this alpha proton, which is the most acidic proton in the system. So the alpha proton will be abstracted and it will lead to the formation of the enolate. So this reaction is a reversible reaction. It is fast reaction. So this is the stabilized anionic intermediate that is forming. Now either it can fold and abstract a proton, resulting in the formation of the product bag, or otherwise, once the once this negative charge will fall on oxygen, this double bond will shift, and X, if it is a better leaving group, it will eliminate, leading to formation of this alpha beta unsaturated carbonyl. And this is a slower step, and hence this is the rate determining step of this reaction. So this is how even CB reaction is taking place. First an enolate will be forming, and later on, once the enolate is falling back, the X which is present, which is a good leaving group, it will get eliminated, leading to formation of the alpha beta unsaturated carbonyl. Okay.
Yes, ma'am.
So for this week 4, you can follow Claydon Organic Chemistry chapter 12 and chapter 19. So I am having the Claydon Organic Chemistry that was released in 2000. So in that it is chapter 12 and chapter 19. Okay. So I will show you the textbook whichever I am having. So this is the textbook I am having. Okay.
Yes, ma'am. This is the first edition, I think.
Okay. So here, chapter 12, that is nucleophilic substitution at carbonyl group, and chapter 19, elimination reaction. For even CB and all, you can follow this chapter 19. Okay.
Ma'am, chapter 19 name was?
Chapter 19 was elimination
Yes, ma'am.
reactions. Clear?
Yes, ma'am.
Okay. Now coming to question number 1. Acetyl chloride can't be obtained by treating acetic acid with A. PCl5, B. CHCl3, C. SOCl2, D. PCl3.
Ma'am, option 2.
Option 2, CHCl3 is the right answer. So when we are treating this acetic acid with PCl5, SOCl2 or PCl3, it will result in the formation of acetyl chloride. So I will be discussing the mechanism for each of these. And in case of CHCl3, such a mechanism is not possible, and hence CHCl3 will not result in formation of acetyl chloride when treated with acetic acid. So we are having acid. So if we are having SOCl2, what is happening? This carbonyl carbon will go and attack on the sulfur, and Cl minus will leave, leading to formation of O, S double bond O, Cl, OH plus. Then the Cl minus can come and attack on this carbonyl carbon, leading to formation of the tetrahedral intermediate. Okay. And now this lone pair, once it will fold, and elimination of SO2 and HCl will take place, leading to formation of acid chloride. Okay, so this is how carboxylic acid is reacting with SOCl2, that is thionyl chloride, leading to formation of acid chloride. Okay, now how it is reacting with PCl5 we will see. It is also following a similar mechanism. We'll write with a different color. OH, this is PCl5. One of the chlorine will leave, leading to formation of PCl4 double bond O H plus, then Cl minus will come and attack on the carbonyl carbon, leading to formation of the tetrahedral intermediate. Now, so this is the tetrahedral intermediate. Now once this oxygen lone pairs will fall back and elimination of minus POCl3 and minus HCl will take place, leading to formation of acetyl chloride. Okay, so this is how PCl5 will react with acid, resulting in the formation of acid chloride. Okay, this is reaction with SOCl2. This is reaction with PCl5. Now we will see reaction with PCl3. It is also following a similar mechanism. Okay, OH in the presence of PCl3, Cl minus will leave, leading to formation of O PCl2 double bond OH plus. Now Cl minus can add on to the carbonyl carbon, leading to formation of the tetrahedral intermediate O PCl2 Cl OH. Okay, now this will get eliminated, that is PCl2 OH will get eliminated, leading to formation of the acid chloride. Like this, Cl, Cl, OH. This will be the byproduct. Okay. So SOCl2, PCl5 and PCl3 can react with acetic acid leading to formation of acetyl chloride. But in the case of chloroform, such a reaction mechanism as we have seen here is not possible. Because of that, here chloroform will not react with acetic acid leading to the formation of acetyl chloride. So the right answer will be CHCl3. Clear?
Yes,
Yes,
ma'am.
ma'am. Okay. So now coming to question number 2. The correct order of IR stretching frequency of the C double bond O in the following molecules is
Option D.
option.
D. Fourth one.
Okay, 2, 1, 4, 3. That is the right answer. So what will be the reason for that? So here this when we consider the electrophilicity or of this carbonyl center, this fluorine being an electronegative atom, it will be inductively minus I effect, inductively pulling the electron density towards it. So this carbonyl CO bond will become shorter. Similar is the case with Cl minus. It is also having minus I effect. But when we consider the case of CH3, it is having a plus I effect. In the case of OCH3, OCH3 is having a minus I effect because of the electron negative nature of oxygen, and it is having a plus R effect like this. Okay. So, if minus I effect is present, the electron density will be pushed towards this fluorine or chlorine, and because of that, this carbonyl bond become shorter. If the bond becomes shorter, then the IR stretching frequency required will be more. Like if we see the case of um, like C single bond C, C double bond C, and C triple bond C, this will be shorter compared to these two. Okay, so this will be having a greater if we consider the formula mu equal to 1 by 2 pi root of k by mu. Here the force constant will be greater for C triple bond C compared to C double bond C and C single bond C. So in this case, when the bond becomes shorter, so the bond strength will be more in that case. So the force constant will be increases, and hence the stretching frequency will be increasing. Okay. So in the case of minus I effect, the bond is becoming shorter, and because of that, this trend is following. So fluorine is having a greater electronegativity than chlorine and oxygen, and because of that, here the minus I effect will be more pronounced. In the case of chlorine and oxygen, oxygen will be having more electronegativity than chlorine. However, here a plus R effect is also involved. Because of that, this will be having a partial double bond character. Okay, so that is why here the chlorine will be having a more pronounced effect than this ester. Okay.
Ma'am.
Yeah.
Ma'am, why minus I effect makes CO bond shorter?
Like the electron density will be pushed towards this electron density. So because of that, that bond will be becoming shorter. Okay. Here it will be like, if we consider the electrophilicity also, here the electrophilicity of the sender will become, electrophilicity will be decreasing. So because of that, this bond will be comparatively shorter compared to other cases. In this case, here the density will be, so this bond will have a triple bond sort of nature. Okay. But in this case, here the electron density it is giving towards it, so this bond strength will be decreasing. Is it okay?
Yes, ma'am.
So here the factors, important equation that we have to consider is of this frequency. So mu equal to 1 by 2 pi root of k by nu, where k is the force constant and mu is the reduced mass, which is m1 m2 divided by m1 plus m2. So if the force constant is increasing, the frequency will be increasing. Okay. So in our case, since the bond is becoming shorter, here the force constant is increasing, and because of that the frequency is increasing. And if some lighter atoms are present, the frequency will be increasing, like we have seen in the case of C double bond C, sorry, like we have seen in the case of CC and CH. Okay. So here CH will be having a greater frequency, IR stretching frequency than CC. So that is because of the presence of lighter atoms. So heavier atoms will be vibrating slowly than the lighter atoms, so their frequency will be decreasing. So these factors have to be considered while we will be considering the IR stretching frequency of the molecule. So in our case, we are considering the carbonyl stretching frequency, and for carbonyl stretching frequency to increase, there should be the presence of a electron withdrawing group, or we can tell like an electronegative atom. If it is present, that will be pushing the electron density towards it by means of negative inductive effect, minus I effect. And because of that, the carbonyl oxygen bond will be becoming shorter, and because of that reason the force constant will be increasing and the IR stretching frequency will be increasing. But if an electron donating group is present, that will release the electron density towards the carbonyl carbon, so that CO bond strength will be decreasing, and because of that the force constant will decrease and the frequency will be decreasing. Okay. So that is the reason why option 4 is the right answer in this case. Is it clear?
Yes, ma'am.
So option 4 is the right answer. Now coming to question number 2. Which of the following have the highest pKa value? Chloroacetic acid, bromoacetic acid, iodoacetic acid, or fluoroacetic acid? So here they are asking for highest pKa value, right? So if pKa, in some problem with this.
Ma'am, option D,
Option
fluoroacetic acid.
fluoroacetic acid is wrong answer. The
Ma'am, iodoacetic.
iodoacetic acid will be the right one.
Okay.
So we will see the reason why. So pKa, sorry, why? So pKa is actually minus log K, right? So K is the acid dissociation constant. As Ka increases, acidity will increase. Okay? And since pKa is minus log K, so for pKa, if it will increase, the acidity will be decreasing. K is the acid dissociation constant. If Ka increases, acidity will increase, and pKa if decrease, acidity will be increasing. So stronger acid will have a lesser pKa and weaker acid will have a more pKa. Okay?
Yes, ma'am.
So if we consider the case of, these are the fluoroacetic acid, FCH2, my pen is having some problem. We will try. Sorry, one second. FCH2, FCH2, C. Sorry for the trouble. FCH2. Just wait for 1 minute. Let me try to figure it out. So if we are having FCH2, COOH, Br, so I will explain, that will be better. So in the case of FCH2, COOH, so we will be having the conjugate base that will be formed. So conjugate base will be FCH2 COO minus, right?
Yes, ma'am.
So that negative charge on COO minus will be stabilized because of the electron withdrawing power or electronegativity of fluorine atom, it is greater. So the negative charge that will be formed on the conjugate base, that is COO minus, will be stabilized by the electronegativity of fluorine atom. So this fluoroacetic acid, it will be having a more acidity than acetic acid, because fluorine will be stabilizing the conjugate base that will be formed. But in the case of chloro, bromo, iodo, etc., the electronegativity will be decreasing, right? So that power to stabilize the conjugate base that will be formed will be decreasing from fluoro to chloro to bromo to iodo. So the least stabilized conjugate base will be that of iodoacetic acid. So because of that, the acidity of iodoacetic acid will be lesser, because the conjugate base is less stabler in the case of iodoacetic acid. Okay?
Yes, ma'am. Ma'am,
Yeah.
for checking the acidity among these four options,
Yeah.
ma'am, we also see sometimes the size of the groups. So here, first we see the size, and then we see electronegativity, then resonance. So are we not going to see the size for fluorine, chlorine, bromine, iodine down the group?
No, no, but these are not living, right? These are not living groups, right? So here we are, for seeing acidity, we will be mostly considering how it is stabilizing the conjugate base that will be formed.
Okay, ma'am. Understood, ma'am.
Okay. So here in the case of iodoacetic acid, the iodine will be having least electronegativity, and because of that, its stabilizing power on the conjugate base will be lesser. So the conjugate base will be less stable in the case of iodoacetic acid. So iodoacetic acid will have the least acidity. So we have seen that pK equal to minus log Ka. So if acidity is decreasing, then the value of pK should be increased. So here they have asked for acids which are having the highest pK value. So here iodoacetic acid is the least acidic, and because of that it will have a highest pK value. Okay? Any doubt?
No, ma'am.
So iodoacetic acid will be the right answer. Now coming to question number 4. Which of the following acids has the smallest dissociation constant? So they are asking Ka value. Ka value where it is coming least. So you have to see which is the least acidic in this case. We have seen that K equal to minus log pK equal to minus log Ka. So if Ka is decreasing, acidity will be decreasing. So you have to find the least acidic among the given acid.
Ma'am, option C.
Option C will be the right answer. So what is the reason for that?
Ma'am, bromine is less electronegative than fluorine, and moreover, it is at larger distance as compared to fourth one. So it will be less stabilizing the conjugate base formed.
Yeah, that is the right answer. So we have seen in the previous case that if electronegative atom is present, that electronegative atom will be stabilizing the conjugate base that will be forming. Right. So that conjugate base should be more stabilized such that the acidity of the compound will be greater. So in the case of this option A, B and all, here fluorine is present. So fluorine, uh, uh, because of its electronegativity, it can stabilize the conjugate base in this case, and because of that its acidity will be greater. So K value will be more. In this case it is one atom away. So because of that, the stability of the conjugate base will be lesser compared to the first case. And in these two cases, here the bromine, which is an electronegative atom, it is present adjacent to this carboxylic acid, and because of its electronegative electron withdrawing ability according to inductive effect, it can stabilize the conjugate base that is formed here. Whereas in this case, the bromine is present further from the COOH, and because of that, here the stabilizing ability of this bromine will be lesser, and the conjugate base is least stabilized in this case. So the conjugate base least stabilized means it will be less acidic. So if it is less acidic, the Ka value will be least in this case. Okay.
Yes, ma'am.
So this is acid dissociation constant. It is used to distinguish strong acid from weak acid. So for strong acids, they have higher Ka values, and the Ka value is found by looking at the equilibrium constant for dissociation of acid. So as Ka increases, the more the acid will be dissociating. Okay. So this is the formula for Ka. Ka equal to concentration of H plus into concentration of A minus divided by concentration of Ha. So if Ka value should increase means this concentration, that is concentration of Ha and concentration of A minus, should be increasing, right? So the more the acid will be dissociating, or more stronger the acid, then only the concentration of H plus in the medium will be more. So the stronger acid will be having a higher Ka value. So in this case, they are asking for a smallest dissociation constant, which means the acid which will be having the least Ka value. So this is the acid which is having the least Ka value, because the conjugate base here formed will be less stabilized compared to the other cases. So option C is the right answer in this case. Is it clear?
Yes, ma'am.
Now coming to question number 5. Actually, I don't know what is problem. My pen is not properly working. It is given that the following compound has a higher pK value than benzoic acid, with the most stable substituent group X, or which is the most probable substituent group X of the compound. So they told that it is having a higher pK value than the benzoic acid. Okay, so it should be least acidic than the benzoic acid. So what should be the substituent that is present on this what should be the substituent X that should be present here, such that it will be having a higher pK value than the benzoic acid. So the substituents, that is X, they have given is OH, Cl, Cn and NO2.
Ma'am, OH.
So what is the reason
Yes,
for that?
Ma'am, because it shows plus R effect, so it will donate electron, it will destabilize the conjugate base, and therefore it is less acidic than benzoic acid.
Yeah, that is right option. Yeah, in the case of NO2, cyano, chlorine, etc., if we consider NO2 and cyano, these are electron withdrawing groups. One second. So this these two are electron withdrawing groups. Okay, this NO2 and cyano are electron withdrawing groups. But in the case of chlorine and OH, it can have lone pair of electrons that can engage in resonance, and it can have minus I effect as well. In the case of OH, or since oxygen is electronegative, it can have minus I effect. Similar is the case with chlorine. Because of the electronegativity of chlorine, it can also have minus I effect. And because of the lone pairs present on chlorine and oxygen, they can also have plus R effect. But in the case of chlorine, this plus R effect will be less pronounced, because lone because the lone pairs are present in the 3p orbital of chlorine. So the overlap such that the resonance will take place will be less pronounced in the case of chlorine. But in the case of oxygen, the lone pairs are present in the um, 2p orbital. Because of that, resonance effect will be more pronounced than the minus I effect. Okay. So here this OH is having uh, plus plus R effect more pronounced than minus I effect, and because of that reason it will donate electron pairs into the ring, making the conjugate base, that is COO minus, less stabilized, and because of that it will be having a higher pK value. Is it clear?
Yes, ma'am.
So OH is the right answer in this case. Now coming to question number 6. By reacting with Grignard's reagent, other aldehydes than formaldehyde produce addition products. Okay, addition products that include tertiary alcohols, secondary alcohols, primary alcohols, carboxylic acid. So they are asking aldehydes other than formaldehyde. So what will be the addition product that is formed if Grignard's reagent is added to any of the aldehydes other than formaldehyde?
One secondary alcohol.
Secondary alcohols will be the right answer. So if we consider the case of formaldehyde, it is like H double bond O H. Okay, and Grignard's reagent is represented by RMgBr. So here it can add on to the carbonyl carbon, resulting in the formation of HOMgBr. This oxygen will abstract this MgBr. Okay, and R. Now this upon hydrolysis, it will result in the formation of OH, H, H and R. So this is primary alcohol. In the case of formaldehyde, it will result in the formation of primary alcohol. If we are having any other aldehydes other than this formaldehyde, so here this RMgBr can add on to carbonyl carbon, resulting in the formation of this tetrahedral intermediate, and that upon hydrolysis minus MgBrOH, it will result in the formation of this secondary alcohol. Okay, so if we are having any ketone in place of aldehydes, then Grignard can add in this fashion, resulting in the formation of ROMgBr, R dash, R double dash, and this upon hydrolysis, it will result in the formation of tertiary alcohols. So formaldehyde will result in the formation of primary alcohol, any other aldehyde, it will result in the formation of secondary alcohol, and if ketone is present, it will lead to formation of tertiary alcohol. Okay. So here they have asked other aldehydes than formaldehyde, the addition product that will be formed. So we have seen that the answer will be secondary alcohol. Is it clear?
Yes, ma'am.
Okay. Now here we have to see this just I will discuss again. Here these are electron withdrawing groups. So this will have a minus I effect, or it will have minus R effect as well in case of nitro. In case of chloro, it will be having minus I effect, plus R effect, minus I dominates, and here minus I effect, plus R effect, here plus R effect is dominates. Because of that, destabilizes the conjugate base, hence least acidic, pK value will be more. Okay. Clear, right?
Yes, ma'am.
Now coming to question number 7. Identify the intermediate X and the product Y in the following reaction sequence. So we are having this methyl grignard, and it is treated with carbon dioxide in dry ether condition. So we will get an X compound, and that upon hydrolysis it will result in the formation of Y. So here this can be written in bracket. Both are attached to magnesium. So what will be the X and Y that is formed here?
Option A, ma'am.
Option A will be the right answer. So what is happening here? So in the presence of this methyl grignard will add on to this carbon atom of this CO2. It will result in the formation of the CH3 C double bond O OMgBr, which is our X. That upon hydrolysis, it will result in the formation of carboxylic acid and MgOHBr, which is the byproduct. Okay, so this is how carboxylic acid can be formed by reaction of Grignard and carbon dioxide. Okay, first the Grignard will add on to the carbonyl carbon of this CO2, and it will result in the formation of this X intermediate, and that upon hydrolysis it will lead to formation of carboxylic acid, and MgOHBr will be eliminated. So option A is the right answer in this case. Any doubt?
No, ma'am.
Okay. Now coming to question 8. Predict the final product in the given reaction. So this benzoic acid is treated with silver hydroxide and this allyl bromide. So it will result in the formation of P. Here they are asking to find what is P.
Ma'am, is it option C?
Option C will be the right
Option
answer.
C.
So we will see what is happening here. So this AgOH, it is acting as a base. Okay, OH minus will be formed and it will be acting as a base. So benzoic acid in the presence of a base, that is OH minus, this is the acidic proton. That acidic proton will be abstracted and it will result in the formation of this benzoate. Okay, now this benzoate, this O negative, can attack on allyl bromide in this fashion, leading to removal of Br minus, and it will form this ester. Okay, so esterification reaction is basically taking place here. First,
Okay.
first a carboxylate anion will be forming, and that will attack on this allyl bromide, leading to removal of bromine, and it will lead to formation of this ester. Is the mechanism clear?
Ma'am, silver hydroxide acts as a base. Am I right?
Yeah, silver hydroxide is acting as a base.
That O minus attacks on the carbon which is double bonded, and then it leads to felicitation, or that is departure of bromine group,
Yes,
such that it forms an ester.
yes.
Fine, ma'am.
Mm. So option C is the right answer in this case. Is this clear?
Clear, ma'am.
Now coming to question number 9. So we are having this alcohol and it is treated with Jones reagent and then with this diazomethane in diethyl ether. So what will be the product that is forming here?
Ma'am, option D.
Ma'am, option A.
Option A will be the right answer. So what is happening when we treat with Jones reagent? So this is a strong oxidizing agent. So it will directly convert this alcohol, primary alcohol, into acid. And that acid, upon treating with diazomethane, we have seen for esterification reaction. So that acid is treated with diazomethane, leading to formation of methyl ester. Right.
Ma'am, actually, ma'am, the second step, like, will it lead to formation of carbene such that the oxygen attacks the CH2N2, it forms CH3?
I will show the mechanism. One second.
Ah, sure, ma'am.
So if I am drawing the mechanism, so we are having this CH3, CH3, CH2OH. So Jones reagent is CrO3 in H2SO4. Okay. So what will happen here? We can draw like this. This oxygen lone pairs will add on to chromium, and this will abstract the proton from media. This is aqueous HCl medium. Sorry, aqueous H2SO4 medium. Then O, Cr, double bond O, OH, double bond O. Okay. Now a proton transfer can take place. CH3, CH3, O, Cr, OH, double bond O, double bond O, H plus. Now water can abstract this proton and this Cr, double bond O, OH will get removed, leading to formation of CH3, CH3 aldehyde. Okay. Now again, water can add on to this aldehyde, leading to formation of this gem diol. Now gem diol can react with CrO3 in similar fashion. Leading to formation of CH3, CH3, OH, O, Cr double bond O, double bond O, OH. Proton transfer will take place and it will lead to formation of this intermediate. Now water will abstract this proton CrO3H2 will be eliminated, leading to formation of CH3, CH3 double bond O, OH. So this acid is formed by Jones oxidation. So this is the mechanism of Jones oxidation. And the Jones reagent is chromium trioxide H2SO4. Okay. Now we are having CH3, CH3 double bond O, OH. Okay. So diisomethane, it is like CH2. It is existing like CH2 in. So this is diisomethane. So this negative charge on this CH2 will abstract this acidic proton, leading to formation of carboxylate. CH3, CH3 double bond O, O minus, and here CH3 N triple bond N plus will be forming. Now this carboxylate can attack on this methyl, and N2, which is a better leaving group, will be removed, minus N2, leading to formation of methyl ester, O CH3. Is this mechanism clear?
Ma'am, how carbon is having negative charge if nitrogen is more electronegative?
This is existing in this form. Like it can be represented like this fashion also. Okay.
Yes, ma'am.
No, it is resonance structure, right? It can undergo resonance. Am I right?
So once when we this lone pair will fall here, this can give anion on carbon. So that is why how this is formed. Okay.
Yes, ma'am.
So first Jones oxidation is taking place, leading to conversion of primary alcohol directly into carboxylic acid, and in the presence of diazomethane, carboxylic acid will get esterification, like leading to formation of methyl ester. Okay. So here the final product will be this one. Option A. Clear?
Yes, ma'am.
Okay.
Yes, ma'am, clear.
Now coming to question number 10. So the hydrolysis of ethyl ethanoate, ethyl ethanoate will be CH2, CH3, double bondo, OET. So ethyl ethanol, the hydrolysis of ethyl ethanoate in alkaline solution containing O18 labeled water, that is H2O18, followed by neutralization with dilute HCl, gives the only product containing O18 isotope, which will be that this EtO18H, this acids, this acid only, or this acid and this alcohol, which is the right answer.
Ma'am, can you please tell ethyl ethanoate structure?
Okay. CH2, CH3, double bondo, O, CH2, CH3. Or we can easily represent like ET, double bondo, OET. Sorry. This is CH3.
Ah, yes, ma'am. There is no option like ET, the C double bond OH.
Yeah. Because we will be considering this also while naming carbonyl carbon also.
Ma'am, is it option D?
Option B will be the right answer. Because
Last one.
uh, how both will be having.
Oh, okay, okay.
So option B will be the right answer, and we will see
Okay,
the
ma'am.
mechanism for that. So we are having ethyl ethanoate, and they have told it is a alkaline medium with O18 labeled water. So in alkaline medium, what will happen? This O18 labeled water, it will add on to carbonyl carbon, leading to formation of CH3, O minus, OH18 and OET. Okay, because alkaline medium, the proton will be abstracted by the base. And now,
Ma'am, it will be OH2 plus, right? When the hydrolysis happens, so what happens? It will be OH2, 18 OH2 plus.
OH2 plus.
So this oxygen which is 18, isotope 18, it will be having another hydrogen. So which means oxygen gets a positive charge.
It will be having OH2 plus,
Yes, ma'am.
and that since it is alkaline medium, so the base can abstract this proton, and it will lead to formation of this intermediate. So I just write in one step. Okay. Now once this is falling back, OET can eliminate, leading to formation of CH3, double bondo, O18H. Since it is a basic medium, so this proton can be abstracted by the base, and it can exist in this format also. CH3, double bondo, O18, O minus. It can abstract proton from water, So here these both structures, this A and this B, it both can exist, right? This oxygen 18 is scrambled between these two like this proton, it can be scrambled between these two oxygens. So both these structures are possible because of resonance that will be um, happening in the system.
Okay, ma'am.
So because of that only we are getting option B as the right answer. Here ethanol will be not having any oxygen labeling. Okay. So
Yes, ma'am.
this plus normal ethanol we will be having.
Okay, ma'am. Ma'am, one more thing. Previously, you mentioned about that mechanism, right? You mentioned that base will come in abstract proton. The base will be like the H2O18. Am I right?
Yeah. Here
Okay.
this OH18 minus that will be present in the medium. It is alkaline medium, na? So that will be
Yes, ma'am.
abstracting the proton.
Okay, ma'am.
So option B will
Got it,
be
ma'am.
the right answer.
Okay, ma'am.
Now going to question number 11. The relative reactivity of acyl compounds towards nucleophilic substitution are in the order of. So we have been given acyl chloride, acidic acid anhydride, ester and amide. So its relative reactivity order we are asked to write. So while we were discussing the summary, we have gone through the reactivity order of this acid derivatives.
Ma'am, option C.
Option
Option C.
Option C will be the right answer. Acid chloride will be more reactive, then comes acid anhydride, then ester, and then amide. So here, based on the living group ability of the living groups, that is X, if we are considering R double bondo X, based on the living group ability of this X, we are telling the reactivity order of this compounds. So if X, that anion X minus that will be formed is more stabilized, then in that case that will be that reaction will be occurring at a faster rate. So if we consider acid chloride, it will be removed as Cl minus. In case of acid anhydride it will be like RCOO minus. In case of ester it will be like OR minus. In case of amide NH2 minus. So the stability of this living groups, that can be identified by the pK of the conjugate acid of this conjugate base of these living groups anions. If the pK value of the acid conjugate acid will be lower, that anion will be more stabilized. So if we consider this, its conjugate acid is HCl, which is having a pK value lesser than 0. Then comes this RCOO minus, it will be having nearly around 10. This OR minus, alcohols will be having nearly about 15 something, and NH2 it will comes around 35 or something, 30 to 35 range. So based on that pK values, so this this anion stability order we can tell. So if the anion is more stabilized, then it will the carboxylic acid derivative will be more reactive. So in the case of acid chloride, the Cl minus that will be leaving is more stabilized. So because of that, it will be more reactive compared to the others. And in the case of amide, NH2 minus is getting in NH2 minus is the leaving group. It will be less stabilized anion, and because of that, this amide will be least reactive. Okay.
Ma'am, what is the difference between acetic anhydride and ester? Like how like acetic anhydride is much greater than ester? Like because there is an oxygen connecting both the acyl groups, right?
That is correct. But you see, the living group in case of this is the structure. If I will draw the structure of acid anhydride, R double bondo O double bondo R. This is acid anhydride, and this is ester, right? So if we are adding some nucleophile, this will be the living group here. R double bondo O minus. This will be the living group in case of acid anhydride, and the living group in case of ester will be R O minus. Right.
Yes, ma'am.
So we will be considering the stability of both of this.
Okay, ma'am.
So this will be more stabilized because resonance effect.
Resonance is there. Okay, ma'am.
In this case, that resonance is not possible.
It is localized.
Yeah, this is localized, so this will be less stable compared to this one. So because
Okay.
of that, the acid anhydride will be more reactive than the ester.
Yes, ma'am. Okay, ma'am. Got it. Thank you very much.
So option C will be the right answer in this case. So we can consider the stability of these living groups by considering the pK value of its conjugate acids. Okay.
Ma'am, one more thing. Nitrogen is actually like less stabilized, and also because it is less electronegative, that's why it is like least stabilized. Am I right?
I didn't get what you are
Yeah.
asking.
What I am trying to say is amine, right? Amine group, which is acts as a living group.
Hmm.
That is the nitrogen minus charge present on nitrogen atom. That is actually like it is weakly stabilized, right? It is not that
Yeah,
stabilized
yeah.
because it is less electronegative.
Yes.
Okay. Whereas in the case of chlorine, it is electronegative atom,
Hmm.
so this minus charge is more like stabilized.
Hmm. Yes, yes.
Okay, ma'am. Thank you.
Now coming to question number 12. So predict the product of the following reaction. So we are having an anhydride here. It is treated with ethanol and heated. So what will be the product that is forming in this case? Anyone?
Ma'am, option D.
Option D, ma'am.
Option D will be the right answer. So what is happening? Here we are having an anhydride, and ethanol is the reagent that is given. So it will add on to any of the carbonyl carbons of this anhydride. Both are identical. Okay. So this alcohol will add on to this carbonyl carbon. This tetrahedral intermediate will be forming. Then a proton transfer can take place, and this O can be protonated. Now once the lone pair on oxygen will fall, this carbon oxygen bond will break, leading to formation of this acid. Now this upon deprotonation, it will lead to formation of this compound. Okay, this PT is proton transfer. So just reaction of this alcohol with this um, anhydride. Alcohol will add on to carbonyl carbon of the anhydride. Then once tetrahedral intermediate will collapse, it will lead to formation of this, and which upon deprotonation, it will lead to formation of this compound. Is the mechanism clear?
Yes, ma'am.
Okay.
Yes, ma'am.
So option D is the right answer in this case. Now coming to question number 13. Complete the following reaction. compound A, when treated with thionyl chloride, it is resulting in the formation of an acyl chloride, and that upon reacting with B, it is resulting in the formation of this ester. So
Is it option D?
option D is the right answer.
Yes, ma'am.
So acid upon reaction with thionyl chloride, it will result in the formation of um, acyl chloride.
Acyl chloride.
Then that acyl chloride, it can react with this alcohol. So the alcohol will be this one. Okay. So what is the structure of this alcohol? CH3, OH, CH2, CH3. So we will be numbering on this basis 1, 2, 3, 4. So this is a butanol, and in the second position hydroxyl is coming. So it is 2-butanol. Okay, numbering should be in this fashion such that the functional group will be getting the least numbering according to IUPAC nomenclature. So the mechanism is like, we are having an acid in the presence of SOCl2. This carbonyl oxygen will attack on this thionyl chloride, leading to removal of C minus. O is double bond O, Cl. Now Cl minus will add on to this carbonyl carbon, leading to formation of now once the lone pair on oxygen will fall, it will lead to formation of this acyl chloride along with removal of SO2 and HCl. Okay, so this is how acyl chloride is forming, and now we are having 2-butanol in the medium that will add on to here. HCl will remove and it will lead to formation of this ester O. Is the mechanism clear?
Yes.
Yes, ma'am.
Okay. So option D is the right answer in this case. Now coming to question number 14. Choose the correct product in the given reaction. So we are having this compound. It is treated with this SiA2BH DHF and H2O2OH minus. So what condition is this?
Hydroboration
Hydrogen oxidation reaction.
Yeah.
Anti-Markovnikov addition.
Yes, yes. So this is an example of hydroboration oxidation. So according to this, anti-Markovnikov addition of hydroxyl will be taking place. So hydroxyl group will be coming on the least substituted side of the alkene. So here OH will be coming. Okay. So in case of first double bond O CH3, CH3, double bond CH2. So if we consider this boron species, here the syn addition will be taking place, and the borane will be coming. On this side after hydroboration. Then upon oxidation, OH minus, this borane species will be getting replaced by OH. One O double bond O CH3. Okay.
Yes, ma'am.
So this will be the first reaction product. Now upon treating with LH and hydrolysis, what will be the product that will form?
Ester will reduce to primary alcohol.
Yeah, ester will get reduced to primary alcohol. So this
Option C.
option C will be the right answer in this case. LH can reduce this ester all the way to primary alcohols.
Yes, ma'am. Got it.
So option C is the right answer in this case. Now coming to question number 15. So we are having this compound in hand and it is treated with tosyl chloride and triethylamine. So what will be the product that is formed here? If I label this as A, B, C and D, what is the product that is formed here?
Option D, ma'am.
Option
Option D.
option D will be the right answer. So what is happening here?
E1 CB elimination.
Even CB elimination will be taking place. So first, the alcohol that is present here, it will get tosylated. Okay. So in the this is the substrate we are having OH, CH3, double bond O. So in the presence of triethylamine, it is a base. It will abstract this proton O minus CH3 double bond O, which will react with tosyl chloride. So tosyl chloride is S double bond O Cl. So this will add on to SO2 and Cl will leave, leading to formation of sorry,
OTS.
leading to formation of this O S double bond O. So this is OTS. Okay. So this OTS, so here we are making it a better living group, this alcohol into a better living group. Now triethylamine is present in the medium. It can abstract this alpha proton, leading to formation of enolate. And this reaction can be reversible as well, as we have seen in the even CB mechanism. Now this type of arrow pushing is taking place, that is even CB mechanism is taking place, leading to formation of this product. Okay.
Okay, ma'am. Ma'am, one more thing is like attack is favored on the substituted position where there is carbonyl red, so it can undergo the ketonal tautomerism. And by this way, the attack will be felicitated in such a way that the double bond is formed in such a way that the OTS is removed.
Yes, yes.
Okay, ma'am.
So option D is the right answer in this case. So this was all for today. If you are having any doubt on any of the questions that we have discussed,
Ma'am, this reaction is example of even CB mechanism.
yes,
Okay.
even CB reaction.
Okay, ma'am.
If there are no doubts, thank you all for attending today's session. We can meet on next Sunday.
Thank you, ma'am.
Thank you, ma'am. Thank you very much.